Hello, my name is Alex. Welcome to my channel. Last time I mentioned that oxygen flow rate can affect ABG test results. So in this video, I'm going to explain how it works on the molecular level. In addition to that, I hope this video can help you improve your knowledge about hemoglobin. We all know that hemoglobin is kind of protein that binds to oxygen. This in order to explain what's going on with hemoglobin, I have to start with its building blocks, which is L-alpha amino acid. But before I start talking about amino acids, please allow me to introduce an important concept called conjugated acid and base. Conjugated acid and base are a pair of chemical species that can be converted into each other by donating or receiving a proton. For instance, an ammonium ion is acting as an acid and being converted into an ammonia molecule while losing a proton. On the other hand, an ammonia molecule is acting as a base by accepting a proton. Thus, the ammonium ion and the ammonia molecule are a pair of conjugated acid and base. For another example, acetic acid and acetate ion are a pair of conjugated acid and base as well. The conjugated acids we discussed above are weak acids. Their tendency to give away a proton is measured by a value called pKa. This value is mathematically equal to the overall pH when 50% of the conjugated acid molecules have their protons dissociated. The relationship between pH and pKa follows the Henderson Hasselbalch equation. It states that pH equals the pKa plus the common logarithm of the base to acid ratio. If the solution is too acidic, then the predominant form will be the conjugated acid. If the solution is too basic, then the predominant form will be the conjugated base. For instance, most of the ammonium ions will be converted into ammonia molecules and lose a positive charge as they undergo a pH shift from 4 to 12. In terms of amino acids, their amino group, carboxyl group, and some side chains can be converted into acids or bases and carry different charges at a certain pH value. So now let's take a quick look at them. This is an L-alpha amino acid. Many of such molecules can form a polypeptide chain by condensation reaction. Then the polypeptide chain can be folded into secondary, tertiary, and quaternary structures. The folding process of this chain is determined by the side chains on the amino acids. Of course, pH plays an important role because it determines the charges on the ionizable side chains as it is discussed in the previous section. Now let's take a quick review. The pH value determines the predominant form of conjugated acid and base, which in turn decides the charges on the ionizable side chains of amino acids. These charges create or strengthen salt bridges, aka ionic interactions. These salt bridges can affect the structure and therefore the function of a protein molecule. Please keep this picture in your mind and we can move on to the section of hemoglobin. In order to understand the chemistry of hemoglobin, we'd better start with myoglobin because it is essentially one of the 4 subunits in hemoglobin. A chemical structure called heme is attached to a histidine in the polypeptide chain of myoglobin. The central iron of the heme is the oxygen binding site. It will remain at a +2 oxidation state and unlikely to be oxidized as long as the heme is attached to the protein. However, once the protein part is denatured or removed, 2 naked heme molecules and 1 oxygen molecule will form a sandwich-like structure, and the iron will be oxidized. On the macroscopic level, as a result, the color will turn brown. For example, a piece of beef will undergo such a color shift once it is cooked. Nevertheless, for most of the time, both myoglobin and hemoglobin are very stable and therefore not oxidized while carrying oxygen. Yet the oxygen binding process can lead to conformational changes in both heme and protein parts. These changes will not necessarily lead to significant consequences in myoglobin. However, they will positively affect the hemoglobin's affinity to oxygen. This image shows an oxygen binding curve of the myoglobin. The x-axis is the pressure of oxygen, and the y-axis is the percentage of oxygen-bearing protein molecules. Myoglobin has a strong affinity to oxygen. It even readily binds to oxygen when the pressure is low. In contrast, hemoglobin initially has difficulty binding to oxygen. It only displays a strong affinity to oxygen when the pressure is relatively high. This is a result of the communication between subunits in the hemoglobin. More interestingly, once we add acid, carbon dioxide, chlorine ion, or BPG to the solution, the hemoglobin's curve will shift to the right. All these properties of hemoglobin are depending on the changes in the salt bridges within the molecule. There are 13 salt bridges in an ideal deoxyhemoglobin molecule. A BPG molecule in the central cavity forms 5 salt bridges with the tetramer. The 4 hemoglobin subunits alpha 1, alpha 2, beta 1, and beta 2 are connected to each other by 6 salt bridges, and each alpha subunit has 1 internal salt bridge. This image is an oversimplified version of salt bridges between subunits of deoxyhemoglobin. Each bar represents the polypeptide chain of a subunit. There are only 8 salt bridges in this picture because it is impossible to display the salt bridges between subunits and BPG in this drawing style. Ionic interactions is to shield the charges. Fortunately, chloride ions are capable to do this job. A negatively charged chloride ion usually binds the hemoglobin between the positively charged N-terminus amino group on one alpha subunit and the positively charged arginine on the other alpha subunit. The negative charge between two positive charges mitigates the repulsive effect between them and creates new salt bridges that will negatively affect the hemoglobin's affinity to oxygen. Another important effector is carbon dioxide. The N-termini of all 4 subunits are the binding sites. This reaction brings a new negatively charged group to the N-termini. It creates new salt bridges that make the hemoglobin molecule more rigid and therefore results in lower affinity to oxygen. Right now, I would like to take a quick review again before moving forward. First of all, pH determines the predominant form of ionizable side chains of amino acids, which in turn decides their charges. As a result, these charged side chains participate in salt bridges and affect the hemoglobin's affinity to oxygen. Besides, pressure of oxygen decides the conformation of hemoglobin, which in turn affects its affinity to oxygen as well. Okay, that's all you need to know for now, and I'm going to explain how oxygen and protons affect hemoglobin. The answer key to our question sits on these 2 salt bridges. The pKa of aspartate's side chain is approximately 4. It is very low and way off the physiological range of pH, which is slightly above 7. Thus, the side chain will always carry a negative charge. On the other hand, in oxyhemoglobin, the pKa of histidine side chain is approximately 7.1. This pKa value falls in the range of physiological pH. Therefore, according to the famous Henderson Hasselbalch equation, a slight shift in pH will lead to a dramatic change in the electrical charge on histidine side chain. We all know that pH in our lungs is 7.6 and pH in our tissue is approximately 7.2. Let's assume that pKa of the histidine side chain is constantly 7.1. We can plug these numbers into the Henderson Hasselbalch equation and see how the pH shift facilitates oxygen binding and dissociation. Our calculation implies that the aspartate histidine salt bridge is present in 24% of alpha subunits in our lungs, and this number can rise to 44% in our tissue. In other words, hemoglobin has higher affinity to oxygen in lungs due to fewer salt bridges. This makes sense because it is a good approximation of our normal respiration process. However, this is only a part of the truth. You might remember from the previous sections that oxygen binding process can lead to a conformational change. Interestingly, the aspartate histidine salt bridge is affected by this change. In the deoxyhemoglobin, the histidine is held tightly against the negatively charged aspartate. This environment makes the histidine more likely to accept a proton. Therefore, in this case, the pKa of histidine is 8.0, which is relatively high. On the other hand, in the oxyhemoglobin, the histidine is no longer held tightly against the negatively charged aspartate. Consequently, its pKa value drops to 7.1. Let's plug the numbers into Henderson Hasselbalch equation and do the calculation again. We compare the results with the previous one. It is clear that the conformational change, or the pKa shift of the histidine, contributed even more to the oxygen binding and dissociating process than the simple pH shift. Okay, now you have learned how hemoglobin works on the molecular level. We started with the building blocks of protein and ended up exploring the mechanism of hemoglobin effectors. This video has been quite informative. I hope you enjoyed this learning experience. Thank you for watching. See you next time.